Most of this chapter has been on quadratic modeling. We've used quadratic equations, we've solved them with factoring and the square root method and the quadratic formula, and we figured out how to find their max and mins at the vertex and things of that nature. But we're going to look a little bit also at cubic functions. And cubic functions are just functions that have a cubed in them. So their general form would look something like this. ax cubed plus bx squared plus cx plus d. So a cubic function is where its biggest exponent is 3. Now the main thing you need to know for this is how to model it in the calculator. In other words, how to graph some data and figure out a model that will fit that data. So I've already plugged in my calculator some data that represents the number of car thefts in the United States from the years 1983 to 1993. Now I'll go ahead and show you, anytime you need to plug in data, you need to go to Stat. So I go right here to Stat. Then you hit Enter for Edit. And it takes this L1, L2. Okay, that's where you enter data points. So the X values, which is L1, list the years after 1982. So 1 represents 1983 because it's 1 year after 1983. 10 down here would represent 1992 because that's 10 years after 1982, and so on. And then over here on the right, we have the number of motor vehicle thefts. So that's the pattern. And this is actually motor vehicle thefts in thousands. So we're really looking at over 1 million for all of these. Now, first thing I want to make sure you know how to do is look at this data in your graph. So right now, if you just hit your graph, it's blank. It doesn't show you anything. Because there's two things we need to do. First of all, you have to turn on the stat plot. So if you go to second y equals, you see stat plot, you go into plot 1 and turn it on. So you just hit enter as you're highlighting on. Another way you can do that is if you just go to y equals, you see right now plot 1 up here is highlighted. That's because we turned it on. You can also just go up there and see now I've turned it off, or you can turn it back on. You just highlight that and hit enter. So you want to make sure it's highlighted so that it's on. That right there is on for plot 1. And now I want to go to Zoom Stat, which is number 9 down here. Now the good thing about Zoom Stat is it figures out for you what your window should be. You can change that manually under the window button that's right there next to Zoom, but the Zoom Stat will do it for you. So I'm just going to hit enter, and you see it automatically makes my picture show up for me. So that's the data points I've plugged in. Now if you notice, this definitely is not a straight line. It's also not really a quadratic either, because we've got two curves going on. It seems to be curving upwards right here, but then curving back down right here. So that's why we're going to go with a cubic model. So once you see your data and you determine cubic's a good idea, you go to Stat, and instead of hitting enter, you go over 1. And then this is where all our regressions take place. So we've already talked about linear regression number 4, quadratic regression number 5, and cubic is what we're going to do now. So you go to number 6 for cubic. So that brings up cubic regression. Now before you hit enter again and get to see what the equation looks like, one thing you can do to automatically graph this for you is if you go to vars, it's right here next to clear, and then go over 1 to y-vars, hit enter for function, and enter for y1. Now when I hit enter, it's going to automatically plot this for me. It's going to put it in my graph. So I hit enter, and there it gives me the information. And if you notice, you can actually see my window up over here in this area, and it's already got it plugged in for me. So you can see the equation. I plug in negative 2.43 x cubed plus 37.32 x squared minus 70.37 x plus 1043.79. So notice I'm rounding to 2 decimal places when I'm going to write my own. The calculator does it exactly in your y1, but when you have to write it down for me on a test or quiz or worksheet or something, just round to the nearest 2 decimal places. And that's what our equation would look like. That would be an estimated model. So let me just go to the graph again so you can see what this looks like. So you can see this is a pretty good model. It fits the data pretty well. So that's a good cubic regression. Okay, now there are two things you need to know how to answer when it comes to these cubic regressions. The first is, what's the y-intercept? Okay, well, if you look here, the y-intercept is going to be d, because the y-intercept, no matter what letter we're using, is always going to be the number that's all by itself. It's not attached to any x's, so it's going to be the d. So if you look at our equation, it's going to be 1043.79. Remember, the y-intercept always means the amount of y you have when there are 0 x's. So let's remind ourselves what those things meant for our data. If we look at our data, we said y was the number of car thefts in thousands, and x is the years after 1982. So if it's the amount of y we have when x is 0, that means it's the amount of car thefts we would expect in the year 1982, because that would be year 0 or x equals 0. So the y-intercept for this would be 1043.79, and that would be the expected number of car thefts in the year 1982. The other thing you need to be able to do with this is predict what might happen. Now, we covered the years 1983 to 1993. Well, we may want to know what happens in 1994 or in 1995. So, remember, it's years after 1982. So if we wanted to find out what happened in 1995, that's 13 years later. So this is where it's again helpful to know that you've already plugged it in y equals. Because once you plug it in y equals, you can use your table. So to get to your table, you go to second graph. It says table right above there. And here you can plug in anything you want. Well, I said I wanted to know what it is in 1994. That's 12 years after 1982, so I just plug in 12, and I hit enter. So we would anticipate that there would be 1,369.8 thousand car thefts that year. Or if I wanted to check out 2002, which is 20 years later, I could plug in 20. Okay, so this actually tells you something helpful. Our model probably isn't good past a certain number of years. Our model does a good job of showing what happens in the years 83 to 93, but I doubt there's going to be negative car thefts in 2002. So that shows you our model is really only good for a narrow range. So instead of that, let's just look at 1995, which would be 13 years later. So we would expect the car thefts to have gone down again to 1,091.5. So that's how you predict. Now, some people get this confused, so I just want to be very clear. When you are plugging in data points, so when you're given x's and y's you need to plug in and graph, that's when you go to the stat plot. When you go to stat and just hit enter, you'll see all these L1 and L2. That just means list 1 and list 2. So when you're plugging in whole points, that's where you go. If you're trying to plug something into your y function, if you're trying to plug something into your y or into something, that's when you want to put it in y equals, which we have here, and then go to your table, which is second graph. Because here you can't affect the y. When you just plug in an x, and the calculator plugs that number into the function for you, and then gives you the result. So here all you can do is basically plug something into another function. You can't just pick a point at random. You can just pick your x, hit enter, and it tells you your y. So again, 3 things you need to know how to do. You need to be able to put the data into your stat plot and run a regression. You need to be able to find the y-intercept and interpret it in terms of the problem. And third, you need to be able to predict what's going to happen based on that model. And the easiest way to do that is to make sure you plug your equation into y1 and then go to your table and you can plug in whatever year or whatever x value you need to predict for.